Assalamualaikum warahmatullahi wabarakatuh. Okay, I'm Madam N.Aliza.A. Okay, you can call me Madam Aliza. Okay, for now, I will explain more on topic 1 in hydraulic BFC 21103. Okay, so seek topic for this subject. So we have the topic 1, topic 2, topic 3, topic 4, topic 5 until to topic 6. So now we just look at the topic 1, introduction to open channel flow. Okay, so introduction to open channel flow. Okay, so flow in open channel. Okay, so at the end of this chapter, students should be able to define and explain on types and state of flow. Okay, identify types of open channels and define open channels geometries. Okay, so we know that open channel flow is a flow of a liquid in a conduit with a free surface subjected to atmospheric pressure. Okay, so this sketch of open channel geometry. So we just look at here. So this is the flow here. Okay, and this is the free surface and this is the datum. So this is the channel geometry. Okay, so the water flow from this part here. Okay, and these directions. So we can know that this is the T is the top width. Okay, A is for the area of this channel. Okay, and the B is the width, bottom width of this channel, and the Y is the flow depth of this channel. Okay, example here, flow of water in a reverse canal partially flows seawards and drains, and flow of water over land is open channel flow. Okay, actually the open channel flow is flow of water in river, the example. Okay, flow of liquid in conduit with a free surface. Okay, the free surface. Okay, so this is the example here is the stormwater management road tunnel is marked in KL. Okay, and also the Taha River Rapid. So this is the example of open channel. Okay, so open channel here. So this is the river. Okay, and a river also Siberian meandering river. Okay, the meandering here. Okay, so we know that you have learned the fluid mechanics, and also now you will learn the hydraulic. Okay, so comparison between pipe flow and open channel flow. You have learned the pipe flow in fluid mechanics, and now in hydraulics you will learn more about open channel flow. Okay, so look at this is the pipe flow. Okay, in the pipe flow here you have learned in fluid mechanics, okay, the last semester, and this is based on the open channel flow. Okay, so pipe flow, actually fluid completely fill pipes cross section and no free surface. Okay, and for the open channel flow, liquid flow with upper surface exposed to atmosphere. Okay, and fluid flows under pressure. So this is pipe flow. In open channel flow, flow due to gravitational force. Okay, slope influence. Okay, and hydraulic grade line does not coincide with water surface, and hydraulic grade line coincide with water surface. Okay, and maximum velocity occurs at center of pipe flow and open channel. So maximum velocity occurs a little distance below water surface. So the velocity distribution is symmetrical about pipe axis, and velocity distribution depends on channel roughness. Okay, this is the comparison between pipe flow and also the open channel flow. Okay, now we look at the practical application. Okay, flow depths in rivers, canals, and other conveyance conduits. Okay, change in flow depth due to channel control, example is weirs, spillways, and gates. Change in river stage during floods. Surface runoff from rainfall over land. Optimal channel design and others. So this is the practical application of open channel flow. Okay, so flow parameters and geometrical elements. Depth of flow Y is the vertical measure of water depth. Okay, this is the Y here. And the normal depth D. Okay, the normal depth D is here. And depth of flow water is, okay, based on this one. Okay, for most application D is equal to Y. Okay, actually the normal depth D is also equal to Y when the theta here is less and equal to 10%. Okay, and cos 1 degree here, so we get the 0.9998. So we just put here as the 1. Okay, the value of 1. So this is the free surface here. Okay, open channel. Okay, this is SW is water surface slope, and flow Q here, and S0 is the bottom slope. Okay, so this is the parameters that you will learn about open channel flow. So you must know that the discharge flow or discharge Q, okay, is the volume of fluid passing across section perpendicular to the direction of flow per unit time. Okay, so this is the flow or discharge Q. Okay, mean velocity V is the discharge divided by the cross section area. So we know that the equation of velocity is equal to flow discharge divided by area. So V is equal to Q divided by A. Okay, and so the weighted parameter P is the length of channel perimeter that is weighted or covered by flowing water. Okay, so the T here. Okay, T is the top width. Okay, B is the bottom width. Okay, this is the area. And the P is weighted perimeter. So the weighted perimeter is the length of channel perimeter that is covered, weighted or covered by flowing water. Okay, so I just highlight with this yellow here. So this is called the weighted perimeter. Okay, so this is the weighted perimeter to get the value of P. Okay, A is the cross-sectional area covered by flowing water. Okay, so the hydraulic radius is R is equal to AP, is the ratio of the flow area to weighted perimeter. Okay, and hydraulic depth is the average depth of irregular cross-section. So we get the equation of T is equal to flow area divided by top width. So it's equal to A over T. Okay, so this is the surface strain that actually used for the JKR standard here. Okay, the concept here based on the type of channel. Okay, based on the trapezoidal. Okay, and the trapezoidal here. Okay, and the triangular. Okay, the trapezoidal and triangular. Okay, actually the triangular is based on the highlight here. Okay, this is the triangular. Okay, so this is based on trapezoidal. Okay, so this is triangular. Okay, so now this is the type of open channel geometries. Okay, so there are 4 types here, the channel section here. Okay, the rectangular, triangular, trapezoidal, and circle. Okay, so all these types geometries of rectangular, triangular, trapezoidal, and circle. So this is the area. Okay, the formula for the area, formula for the top width, and weighted perimeter P. Okay, so this table will given in your final or in your test. Okay, so the never okay, so no need to worry because all these equation, the formula here is given. Okay, so look at the activity 1.1 is actually an example here. They have the trapezoidal channel. Okay, the trapezoidal channel with the Y. Okay, the Y flow depth is 2 meter, and this one 1 meter, and the B is 3 meter. Okay, so for this activity, to find top surface width T, flow area A, weighted perimeter P, and the hydraulic radius R. Okay, if Q is equal to 2.4 meter cubic per second, determine the state of flow. Okay, so we just jump to the here. Okay, so actually to find the top surface width, weighted area, weighted perimeter, and hydraulic radius, so you can look again based on this here. Okay, actually for this example here, actually you must know that if this trapezoidal is, you must know that this is the 1 over Z. Okay, Okay, so 1 over Z here. Okay, so to get the value of Z, okay, so you can find that because this is 6. Okay, the degrees here. Okay, 60 degree. Okay, is equal to 1 over Z here. Okay, so we know that. So we just use here. Okay, Z, to get the value of Z, 1 over tangent 60 degree. So you get the value of Z is 0.5774. Okay, now to get the T, the top width of this, okay, the top width of this trapezoidal. So we use this formula B plus 2ZY. Okay, so that's why you get the T equal to B plus 2ZY. So you just put all the value here, then you get the value of T. Okay, so now you get the area. Area is also based on the table, okay, based on the trapezoidal. So you get the value of A. So just put the value here, aka put here, and then you get the area here. Okay, so the value of area is 8.309 meter squared. Okay, so the area. Okay, so to get the P weighted parameter is also, you can refer also to this here. Okay, because using the trapezoidal. So this is area. So this is the top width, this is the weighted perimeter. So you use the trapezoidal here. Okay, and just look at the activity here. So you get the value, the P here. Okay, so just put the value here until you get the value of P here. Then you use the R is equal to A over P. Okay, so you get the R is equal to 1.091 meter. Okay, so if Q is equal to 2.4 meter cubic per second, they give you the here. Okay, so you get the value here. Okay, so the V velocity, we know that velocity is equal to Q over A. Okay, you get the velocity 2.4 divided by 8.309. So you get this value. Okay, so to know that the state of flow, okay, the state of flow, so you must refer to, sorry, okay, we just jump to this slide. Okay, so we just look again to the types of open channel. Okay, the types of open channel, they have the prismatic and non-prismatic channel. Okay, prismatic channel is the channel which cross-sectional shape, size, and bottom slope are constant. Okay, most of the man-made artificial channels are prismatic channel of a long stretch. Example of man-made channels are irrigation, canal, flume, drainage ditch, roadside gutters, drop, chute, cover, and tunnel. So this is the example of man-made channel or prismatic channel. Okay, all natural channels generally have varying cross sections and therefore are non-prismatic. So example of natural channels are tiny hillside, rivulets, through brooks, stream, rivers, and tidal estuaries. Okay, Okay, so this is the natural channel and also the prismatic channel. Okay, the types of open channel. Okay, so the rigid and mobile boundary channel. Okay, rigid channels are channel with boundaries that is not deformable. Okay, channel geometry and roughness are constant over time. Typical example are line canal, sewers, and non-erodible unlined canal. So mobile boundary channel are channel with boundaries that undergo deformation due to the continuous process of erosion and deposition due to the flow. Okay, example are unlined man-made channel and natural river. Okay, actually for this type of open channel, so actually this based on the theory in your test or in your final. Okay, so you must know that what is the rigid channel, what is the mobile boundary channel, what is the prismatic or non-prismatic channel. Okay, so this is for theory. So canal is usually a long and mild slope channel built in the ground, which may be unlined or lined with stone masonry, concrete, cement, wood, or bituminous material. Okay, so this is the example here, canal. So this is called canal, or in Malay called terusan. Okay, so terusan Wan Muhammad Sama in Kedah. Okay, so this is the example here for canal. Okay, and also in Russia. Okay, in Russia here, this is the canal, or in Malay it's called the Rusan. Okay, so flumes. Okay, flume is a channel of wood, metal, concrete or masonry, usually supported on or above the surface of the ground to carry water across a depression. Okay, so this is called flumes. Okay, this flume diverts water from White River, Washington to generate electricity. Okay, and also this is hydroelectric project. Okay, so this is also the open channel flume in laboratory. Okay, so you can look at this flume in our labs. Okay, in hydraulic labs. Okay, so this is for experiment. Okay, for open channel. Okay, experiment for open channel. Okay, here is a channel having steep slope. Okay, so they have a natural chute have the fall here. Okay, ataupun kita panggil in Malay we call air terjun. Okay, so natural chute falls on the left and man-made logging chute on the right on the Quebec, Canada. Okay, so drop is similar to a chute, but the change in elevation is within a short distance. Okay, dia ada this one lah. So this is called spillway in the dam. Okay, actually the diversion in dam. So it's a vertical hard basin drop structure designed to dissipate energy. So we will learn more on hydraulic structure in chapter 5 or chapter 6. Okay, so for the hydraulic structure, this is called the hydraulic structure. Okay, so stormwater sewer is a drain or drain system designed to drain excess drain from paved street, parking lots, sidewalls, and roof. Okay, so this is the stormwater sewer, storm drain receiving urban runoff. Okay, storm sewer here. Okay, so the types and classification of open channel flow we can divide to steady flow and unsteady flow. Okay, so steady flow, so also we can divide to uniform flow and non-uniform flow. Okay, so non-uniform flow is rapidly vary flow and gradually vary flow. So the uniform flow, so you will learn in chapter 1, chapter 2. Okay, chapter 3 until chapter 6, so based on non-uniform flow. Okay, so steady flow and unsteady flow. So you have learned uniform flow in chapter 1 and chapter 2. Non-uniform flow, chapter 3 until chapter 6. So based on rapidly vary flow and gradually vary flow. Okay, so open channel flow condition can be characterized with respect to space. Okay, space is how do the flow condition change along the reach of an open channel system. Okay, so for the space, so it's uniform flow. So depth of flow is the same at every section of the flow. dy over dx is equal to 0. Okay, for non-uniform flow, depth of flow varies along the flow. dy over dx is not equal to 0. Okay, so this is for condition respect to space, the uniform flow and non-uniform flow. Okay, so you can sketch here. Okay, depth of flow is the same at the every section, so we get the dy over dx is equal to 0. Non-uniform flow is dx over dy is not equal to the 0. Okay, so the uniform flow, the constant water depth, so the y here to y here is constant, is the same y. Okay, but non-uniform flow y1 is not the same as the y2. So because the dy over dx is not equal to 0. Okay, so respect to time, how do a flow condition change over time at a specific section in an open channel system? So this is steady flow and unsteady flow. Okay, so steady flow, depth of flow does not change and constant during the time interval under consideration. So dy over dt is 0. And unsteady flow, depth of flow change. Okay, so unsteady flow, depth of flow changes with time. So dy over dt is not equal to 0. Okay, so for steady flow here, you can sketch the flow here. Okay, with time 1, t1, time 2, t2. So y1 is equal to y2. So this is called steady flow, because the depth of flow is the same at every time interval. Okay, for unsteady flow, okay, y1 is not equal to y2, is not equal to y3. Okay, because T1, T2, and T1, T2, and T3 is not the same. Okay, so Y1 not same as the Y2 and not same as the Y3. Okay, depth of flow change from time to time. So that is the unsteady flow. So the flow is rapidly varied is the depth change abruptly over a comparatively short distance. Example of rapidly varied flow are hydraulic jump, hydraulic drop, flow over weir, and flow under a sluice gate. The flow is gradually varied if the depth change slowly over a comparatively long distance. Okay, example of gradually varied flow are flow over a mild slope and the backing up of flow backwater. So these two part of the these two types of flow is rapidly varied flow and gradually varied flow. So you will learn in chapter 4 and chapter 5. Okay, chapter 4 and chapter 5. So based on the rapidly varied flow and gradually varied flow. Okay, so this is the concept of the RVF and GVF. Okay, so you will learn more in topic 4, 5. Okay, 4 and 5. 4 and 5. Okay. So now we look at the equation of state of flow. Okay. So after we know that the state of flow here, okay, the state of flow here, so we can go back to the example in activity 1.1 and 1.2. Okay. So the state of behavior of open channel flow is governed basically by the viscosity and gravity effects relative to the initial forces of the flow. Okay, effects of viscosity is depending on the effect of viscosity relative to inertial forces. The flow may be in laminar, turbulent, or transitional state. So we use the Reynolds number represent the effects of viscosity relative to inertia. So we use this formula, okay, using the Reynolds number, okay, to get the state of flow. Okay, so Reynolds number is equal to V is velocity times by the R, okay, the hydraulic radius, divide by the viscosity. Okay, kinematic viscosity. Okay, so where V is the velocity, R is the hydraulic radius of a conduit, and the V is the kinematic viscosity. Okay, for water. Okay, so use this equation or formula for know that the state of flow, whether it's the laminar, turbulent, or transitional. Okay. For laminar, when the Reynolds number is less than 500. Okay. If the flow is transitional, so the Reynolds number is between 500 to 1200, okay, sorry, 12, okay, 1500. Okay, so the transitional, and the flow is turbulence, so the Reynolds number is more than 12,500. Okay, so this based on the Reynolds number here. Okay, so this is laminar, this is the transitional, and this is the turbulent. Okay, so using the Reynolds number formula. Okay, so the flow is laminar if the viscous forces are dominant relative to inertia. Viscosity will determine the flow behavior in laminar flow. Water particle move in definite smooth paths. Okay, the flow is turbulent if the inertial forces are dominant than the viscous force. So in turbulent flow, water particles move in irregular paths which are not smooth. Okay, so this is for state of flow. Okay, effect of gravity. So we use the Froude number. Okay, so using the effect of gravity. So depending on the effect of gravity forces relative to inertial forces, the flow may be subcritical, critical, and supercritical. Okay, Froude number represent the ratio of inertial forces to gravity forces. So using the Froude number here is equal to V is velocity divided by the this one G times by the D here. So the V is velocity, D is the hydraulic depth of a conduit, and the G is the gravity acceleration. Okay, using the value of 9.81 meter per square here, second. Okay, second square here. Okay, so the Froude number less than 1, so this is subcritical state. Froude number is equal to 1, so the flow is in critical state. So more than 1 is supercritical state. Okay, so you just highlight here. This is subcritical state when the Froude number less than 1. Equal to 1, Froude number is equal to 1, so it's critical state. So more than 1, So this supercritical state. Okay, so using the value here. Okay, velocity less than this one, so you use the Freud number. Okay, the regimes of flow based on subcritical lamina when Freud number less than 1 and Reynolds number is less than 500. Okay, supercritical lamina when Freud number more than 1 and Reynolds number is less than 500. Supercritical turbulent, Freud number more than 1 and Reynolds number is more than 12,500. Okay, and subcritical turbulence when Freud number less than 1, Reynolds number more than 12,500. Okay, that's all. Okay, that's all the equation that you will use in this topic 1. Then you must use also that this equation until in chapter 2 until to chapter 6. Okay, now we look again back to the activity or example to get the state of flow here. Okay, so the state of flow. Okay, so using the Freud number, okay, you get the value state of flow to get the Freud number here. Okay, you get the velocity. So you get the velocity, you get the velocity here 0.2888. Okay, so just put here, and then you get the G is 9.81. Okay, to get the D, okay, the D is the A divided by T. So you must find the A over T here based on the previous calculation. So you get the value. Okay, so for using the Reynolds number here, so you get the value here until you get the flow is laminar, turbulent, or transitional, or using the Reynolds number. Okay, and using the Freud number to get the supercritical, subcritical, or critical. Okay, so you try to calculate again and find the value of this state of flow. Okay, you try. Okay, now you look at this example or activity 1.2 here. They have the channel here. Okay, so the channel here, so we get the one. Okay, A1, A2, A3, A4, and A5 here. So 1, 2, 3, 4, 5. So there are 5 types of channel here. Okay, this is the triangular channel. This is the rectangular channel. A2, A3 is also rectangular channel. A4 is also the rectangular channel. And A5 is triangular channel. Okay, so you must find the flow area A. So to get the flow area A, so you must get the A1 plus, okay, A2 plus A3 plus A4 and plus A5. Okay, so you just find here. Okay, with the parameter hydraulic radius. So you just look here. Okay, so you just look here. Okay, to get the area here. So you must get the area 1. Okay, for this calculation, I just put first at the A5 here, plus A2 plus A3 plus A1, 4 and plus A1 here. Okay, so Z1 is 1 and Z5 is also 1. Okay, so you must get here. Okay, to get the A1 here, to get the value of Z, so you must know that the 1 over Z here. Okay, so to get the Z here, so you must know also 1 over Z. Okay, so this is the Z. Okay, so you know that the Z is actually this is 1 meter, and also the height is also 1 meter. So 1 meter to Z here. So 1 meter to 1 meter. So the Z for A1, so you get the Z for A1 Z1 here. So you get the 1. Okay, for Z5 here, okay, the Z for 5 here, you know that the 1. So you know 1 over Z is equal to the 1 here is also the same as 2 here, 2 meter. Okay, as the same as 2 meter, so you get the 2 meter. Okay, and the Z here, okay, the part here, okay, and there's 2 meter also, okay, because this is divided by 2 here. Okay, this is 2 and this is 2. Okay, so you get the divide by 2. Okay, so the Z is also the 2 here. Okay, to get the value of Z, so Z 5. This is Z5. Okay, okay, to get the Z5, okay, you also get 2 over 2. Okay, so that's why you get 1. Okay, so that why you get the Z5 is also 1. Okay, so A1, A5, A2, A3, A4, and A1 here. So the A5 here is Z5, Y. So you must look again at the type of here. Okay, using the triangular. So this is triangular. So you must look at this one. Okay, so you must look at the triangular here. So you just put the area, put the top width, and also the weighted perimeter. So use this equation for triangular. Okay. Okay, so this triangular. Okay, and the A2 is the rectangular. Okay, and A3 also the rectangular. A4 also the rectangular. And the A1 here also the half of the triangular. So that's why 1 over 2 B1 times by Y1. So using the, okay, for the triangular, the half of the triangular. So this one is using the triangular. Okay, so you just put all the value until you get this value of A. So the weighted parameter, also weighted parameter of P5 here. Okay, weighted parameter that I highlight by the value here. Okay, the highlight of the red here. Okay, A1 and this, okay, to here and this one. Okay, so this is the weighted parameter. Okay, so weighted parameter for the A1 here, okay, A2 here, and A5 here, A4. Okay, so that's why at weighted parameter P5, weighted parameter in P5, P3, P4, and P1 here. Okay, so use the the formula for the weighted parameter in types of this channel and this channel and this channel and also this one. Okay, so you just put the value here until you get the value of P, weighted parameter is 17.07 meter. Okay, so then you get the hydraulic radius R is equal to A over P. Okay, just put the A divided by P, so you get this value. Okay, so this is the calculation step by step that you must find the area, you must find the weighted parameter, you must find the radius. Okay, and then you will also use this formula in chapter 2, chapter 3, chapter 4 until chapter 6. Okay, so this is the basic formula that you must know and must understand, because you will also use this formula in all this semester, okay, until chapter 6. Okay, so that's all. We have finished our chapter 1 based on open channel flow, equation, and so on. Then so we see you in chapter 2. Okay, that's all. Thank you. Assalamualaikum warahmatullahi wabarakatuh.